Hi, and welcome to another video about Probability Theory of the Logic of Science by Jaynes. This video will cover Chapter 5 called Queer Uses for Probability Theory. Queer in this sense meaning strange, unusual uses for probability theory. This chapter is a very fun chapter. It's an exciting one. It's a little bit of a break in the flow of the book, and I think that the point of it is to serve as something of a kind of diversion or some comic relief because it's got some kind of fun examples in it. Up to now in the theory of the book, we've built up this nice kind of probability theory and tools of hypothesis testing, and we've really only been able to apply those to very kind of particular contrived examples with certain well-defined properties. Okay, things like our widget testing example and sampling with them without replacement. And I think that the purpose of this is to give you a sense of what other kinds of problems are out there that you might be able to reason probabilistically about. Okay, so we're going to return to those kind of dry examples when we get back into things like parameter estimation and significance testing, which is what comes next. So I think this is just kind of a break in that flow. But I also think that in some sense it's very important because it shows how probabilistic reasoning, and in particular the reasoning of hypothesis testing and probabilistic inference, can be useful in real-world situations where maybe the assumptions and the properties of the propositions that we're dealing with are not so well defined and contrived as they are in the kind of widget testing and urn drawing examples that we've done before. And I think that, so in that sense, what it kind of shows us is how we would actually use this reasoning in a real problem where we're actually bringing to bear all of the assumptions and the background experiences that we have, and not just kind of what's assumed for the sake of doing the problem. Okay, so I think in that sense it's a very important chapter. I also think that one of the kind of lessons of it that we'll see is that different people approaching the same problem or the same situation they're trying to understand might be led to completely different conclusions just as a function of the background information they bring to the problem. So that's also one of the kind of interesting conclusions that comes out of this, is that people may be reasoning rationally and yet come to different conclusions just because they've had different lives up to that point. And probabilistic reasoning can kind of encompass all of that. Another one of the I think important things that gets played out in this chapter that's very interesting is that up to now, Jaynes has been, I think, a little bit cagey and unclear about this program of probabilistic reasoning in terms of whether it's a descriptive one, meaning just a codification of the ways that we reason and kind of writing them down in a formal system, or whether it is meant to be prescriptive or normative one in the sense of telling us how we should reason and what good and bad reasoning kind of looks like. And I think that in the course of kind of working through these examples, which are real historical examples of people reasoning about uncertain phenomena, the point kind of gets articulated that there are some of these where we'd say people reasoned correctly, and then some of them where we might say they reasoned incorrectly. And the point is that with the language of probability and with the tools of the rules of probability and hypothesis testing, etc., we can kind of articulate that a little bit and break it down and understand the components of the steps of those lines of reasoning, and we can say, okay, these were the parts of this person's reasoning that we want to preserve, and these were the parts maybe that we want to abandon. And so in that sense I think that these examples help us kind of understand the good reasoning and the bad reasoning parts and what we're actually trying to accomplish with this program of probabilistic reasoning. In terms of whether it's normative or whether it's just descriptive. Okay, so we're going to be using common sense, but only kind of where we agree that common sense led us to the right conclusion, and we're going to use that as kind of defense against other bad kinds of reasoning. The kind of one of the main things that we're going to have to deal with then in using probabilistic reasoning in an actual real-world problem is assigning things like the prior probability for a hypothesis. Okay, so start with a product rule where we usually start. And we know that with the rules of probability, they're kind of inferential rules that we've built up to this point, we're able to perform hypothesis testing, so assigning probabilities to a working hypothesis as a function of the prior probability of the hypothesis, so what its probability is conditional on, just our background information, and then a ratio of two things, the sampling distribution of the data, conditional on the hypothesis, divided by just the total probability of the data, unconditional on the hypothesis. Okay, so in the examples we had thus far, these things were kind of easy to work out as consequences of our background assumptions in the statement of the problem. But now we're actually dealing with, okay, maybe we want to reason about some real phenomenon in the world, and X here is actually all of the assumptions that we actually bring to the problem. So kind of our whole history is up to that point. So the real question is, all right, how do you go about assigning things like this prior probability of a hypothesis, okay, or what's often called prior elicitation. Okay, that's just the word for assigning a prior probability based on background assumptions. And this is generally going to be kind of a hard problem. One strategy that Jaynes suggests that can help kind of guide us to do this prior elicitation is to imagine an experiment, okay, that would kind of test this hypothesis, and to actually imagine what the data would be of that experiment, and then just think about what kinds of conclusions would we actually draw, and then kind of work backwards to see what our prior assignment must have been. Okay, so this maybe gets made a little bit more clear if we think about an example. But let's think about the example that Jaynes gives is, so someone named Mr. Smith tells you that he has ESP. Okay, so the hypothesis that we're interested in thinking about is the one where we'd like to test, how likely is it that he has ESP? Okay, whatever that means, and we'll actually just define that sort of unambiguously to mean something like, if you think of a number, let's say 1 to 10, the number is 1 to 10, then Mr. Smith can tell you what number you're thinking of. Okay, what that number is. Okay, always and without error. Okay, so the claim is he's got this ability. We'd like to be able to test this hypothesis, maybe according to some experiment and according to some data, but part of that is going to involve a prior probability that we associate to the hypothesis. So here our X is kind of just everything we know. So everything you know in your life up to the point of Mr. Smith telling you this remarkable fact. And the question is, what is this prior probability P of H given X? And the idea is, well, we can actually kind of suss that out a little bit or draw it out of ourselves if we can imagine an experiment that would sort of pit this hypothesis against another hypothesis where we believe that we know what the sampling distribution and et cetera would be. Okay, so the idea is going to be to pit H against its negation, H bar, in an experiment in such a way that the probability of getting some data conditional on H bar is computable. Okay, and we'll actually see more specifically what we mean by it being computable. All right, so how would that work? Well, let's say that we were able to design the experiment and we could do it in such a way that the only possible way that he could guess the number that we were thinking of is just by kind of pure chance. Okay, so this is kind of what we want our H bar to be in the confines of this experiment. It's just sort of pure luck at guessing whatever number is on our mind. And the way that we might think to do that is, okay, so let's say that for me, this experiment might be something like, all right, I'm going to go to the store, I'll buy a new deck of cards, I'll take out all the jacks and the queens and the kings, so I have aces through tens. I'm going to shuffle that deck of cards up very well. I'll then put Mr. Smith in one room and have him kind of blindfolded and watched by an observer, friend of mine, and then I'll go in another room and I'll shuffle the cards, I'll draw one out, I'll look at the number on the card and I'll think about it, and if he can call out to me from the other room what number it is I'm thinking about, with very tight controls on making sure that there's no possible way he can see what I'm doing, maybe I would come to believe that the probability of him being able to do that is 1/10, okay? Because the numbers go 1 through 10, there are equal numbers of them, I've shuffled it up, and I believe that he doesn't know which card I'm looking at, so the only way he can possibly guess is 1/10. And in fact, if I sort of repeated that, and I believe in the kind of power of randomization, so this sort of magical property that if I put the card back in the deck and I shuffle it, then it kind of makes all the configurations equally likely, and therefore the next time I draw a card out, it's also probability 1/10 that he'll be able to guess it. If I believe in all that, then I might be able to say that, okay, the probability of a set of data conditional on this alternate hypothesis that he doesn't have ESP is something like 10 to the minus n. Okay, and what I mean by the data here is that he guesses n out of n correct. Okay, so I give him n tries, and he gets all of them right, and just on this kind of pure chance hypothesis, my probability assignment to that would be 10 to the minus n, assuming that I've controlled for every possible thing. Okay, now one or two things to note here. First of all, this is not the same as saying that I think the probability of drawing out any particular sequence of numbers is 10 to the minus n. That would be kind of the sampling with replacement argument that we went through a few videos ago. This is actually saying something like my state of knowledge about Mr. Smith's state of knowledge says that he is unable to guess my sequence of n cards with any higher probability than 10 to the minus n. Okay, so this is not just like I'm ignorant of the positions of the cards after shuffling them. I'm also claiming that he is ignorant of the positions of the cards and the sequence that they get drawn out. And therefore, this data probability conditional on this hypothesis of him not having ESP is this low number 10 to the minus n. Okay, so it's really about my background assumptions about what another person knows or what their state of knowledge is, not just about my own. Okay, the second thing to note here is that actually we've been a little bit unfair here, because we've said that our working hypothesis is he's got ESP, that's what we're kind of interested in testing, and our alternative to that is maybe that he doesn't, but that doesn't necessarily mean that the probability would be 10 to the minus n, so we've excluded kind of any middle ground where maybe he's able to guess, but just at a slightly higher rate than chance, pure chance, but not at the perfect rate of getting them all right all the time. So really, there should be some kind of partial ESP hypothesis that could split the difference between the two, and we'll come back to this when we talk about the Soal-Golding experiment in just a few minutes. But for now, let's just say that our background assumptions X exclude all middle ground possibilities. So either he has the ability to tell us what the number is, or he does not, and he's just guessing, and his probability of guessing is 10 to the minus n. Okay, so far so good? All right, so this gives us then the sampling distribution for this set of data, and we know actually what the sampling distribution on our hypothesis would be, and that's just 1. Okay, so we've opened ourselves up to the possibility that he's able to tell us with certainty what card we're thinking about, so the probability of him being able to do that conditional on the hypothesis is 1. If we now think about then plugging these things into our product rule of probabilities and doing our kind of hypothesis test on based on this observed data, or what would it tell us? Well, first of all, we'd have an expression like this for the posterior probability of the hypothesis. We'd have another one for the posterior probability of the negation of the hypothesis, so that would be whatever our prior for the negation was, times our sampling distribution shown here, divided by P of D, given X. That's just product rule for the negative hypothesis. If we do the thing from the binary hypothesis technique and divide one of these by the other one, we get this kind of nice cancellation. So we can say that the odds, okay, of the hypothesis posterior to the data are like the odds from the prior probabilities, so just prior probability divided by probability of its negation, times this ratio, where the ratio is the kind of likelihood ratio, okay, how likely the data is given H, divided by how likely it is given H bar. And we actually know what those things are. So we have our kind of prior odds. We have probability of the data given H is 1. Probability of the data given H bar we said was 10 to the minus n in this perfectly controlled experiment. And so this is something like odds from the prior assignment times 10 to the n power. Okay. If we then take logs of that and think about things in terms of our evidence decibel scale, we might say that our evidence for the hypothesis given this observed data is whatever our prior evidence was, okay, plus 10 times n. Okay, so we take log of that and we multiply by 10, we get n times 10. Okay, so now this is really the point. If we get to this point, we still don't know what our prior assignment was, so we're not able to actually do the hypothesis test. But what we can say is, okay, what value of n would make you uncertain about this hypothesis in light of the observed data? Okay, so if you actually did this, you had this controlled experiment, you'd made sure that you'd eliminated all other possible explanations. He was able to guess n out of n correct for some value of n. At what point would you start to kind of wonder about whether he actually had ESP? And in particular, we can phrase that in terms of what n makes this posterior evidence about on the order of 0. Okay, so when we have an evidence of 0, that means our probabilities are about a half, so we're basically 50-50. We don't know whether he has ESP or he doesn't, because we've seen some evidence that's gotten us to the point of really seriously considering this as a hypothesis. Okay, whatever that number is, okay, if it exists, then it must be the case that your prior evidence for the hypothesis was minus 10n, right? Okay, because if when you add 10 into something, you get a number that's about 0, then it must be the case that that number was about minus 10n, which means, just putting things back in terms of our odds scale, that our odds are about 10 to the minus n for whatever that n is, and so our probability is also about 10 to the minus n. Okay, so maybe a very small number, something not 0, and basically you can kind of draw it out of yourself by imagining doing this experiment and getting this value of n that would actually force you to be uncertain. Now Jaynes says his probability for our ESP would be something about minus 100 decibels, so he would require 10 successful guesses in a row to make this something he would seriously consider. That's an odds of, so 100 decibels is odds of 10 to the 10th against, right? So 10 factors of 10. 10 to the 10th against is 10 billion to 1 odds against. Pretty steep. I think for me personally it might be a little bit lower than that. I think if somebody got maybe 7 or 8 correct, I would probably seriously consider that they might have really something going on. And so my prior assignment might be something more like minus 70 or minus 80 decibels, okay? 10 million or 100 million against, odds against, about on par with predicting tomorrow's lottery draw. Okay, that's another way you can kind of imagine this. All right, so anyway, whatever it is, if you have such a number, right, you're not totally dogmatic about the possibility that even after an extremely large number of guesses correct, you would always just say that he's extremely lucky and that he doesn't have ESP. If at some point you would actually be uncertain about this working hypothesis, then you must have a prior assignment that is some number out there at minus 10n decibels, whatever it is. Okay, so then the big question is, all right, let's say somebody actually did this. Right? They did this experiment. You weren't maybe there personally in charge of everything, but someone described the experiment to you, and they said, yeah, I set up all the controls that you asked me to do, and I did the experiment, and I got a very large number n. Mr. Smith guessed n numbers correctly in a row, where n is some very large number. Would you then actually conclude with certainty or with near certainty that he does have ESP? And if not, why not? All right, what else is going on here that prevents you from just following this hypothesis test in this binary example out to its logical conclusion, which is that the larger this is, the more certain you are in the hypothesis. And basically, this is the situation that a number of people in the scientific community were faced with. So around the early 40s, there was a series of experiments that claimed to show that people had ESP under very controlled circumstances with extremely high probabilities, posterior probability assignments. And the question was, all right, do you accept that? Right? Do you take that as strong evidence that people in the world have ESP? Jaynes mentions this as kind of one of the classes of examples of things that we're able to reason about. I think it's actually kind of the most interesting one, and it has in it all of the main ideas from the chapter. So I think we're just basically going to talk about that today and really go through that example in detail. But I think you'll see that the principles are kind of generally applicable. So this was what's called the Soal-Golding experiment. Okay. And the story was basically like this. So Samuel Soal was a British mathematician, lecturer in math and statistics and other things in the kind of early part of the 20th century. And he had, unfortunately, something very tragic happened to him, which was that he had a brother who was killed in World War I. Very kind of common experience, all too common. And like a lot of people at the time who had lost family members and loved ones in the war, he became very interested in the occult and in spirits and in seances and psychic mediums and things of this nature. So he started getting very interested in something called parapsychology, which is the kind of psychology of paranormal phenomena. Okay, so things like telepathy, ESP, like we're talking about. And what kind of made him different from his contemporaries, other people who were interested in this at the time, was that he had this training in statistics and mathematics, and so he went about his studies in what we would kind of recognize as a scientific way. So he started performing controlled experiments and actually having these people who claimed to be psychics try to demonstrate their abilities in a way that was experimentally verifiable. Okay, I think he was looking maybe for some kind of rigorous proof that these things worked and that they were able to gain knowledge of things that they shouldn't be able to gain knowledge of. And he searched for, I think, many years, basically in vain, to find people who could do this in a controlled experimental setting. And he ended up really focusing on a system of experiments called card guessing. Okay, so what that consisted of was having someone who had ESP sitting in some lab environment and trying to guess the symbol or number on the back of a card, and then comparing those frequencies against chance. Okay, so basically like what we were doing with this Mr. Smith experiment. And again, he worked at this for many years, and eventually he found what he thought were a couple of people who were actually able to do it, right? So they were actually able to show some success in card guessing significantly above the chance expectation. And one of the people he worked with was a woman named Gloria Stewart, okay, who was one of his kind of ESP agents who claimed she had ESP. And basically, around 1941 to 43, they did a series of experiments with her and one of the other people that claimed to show this positive deviation, okay, this actual significant positive effect of being able to guess the symbols on the backs of cards. What that consisted of and the kind of setup of the experiment was this. So basically what he would do is he would write down or produce by some means a series of random numbers between 1 and 5. Okay, so he had these numbers 1 through 5 in some sequence, undisclosed, and kept under very tight controls in his possession all the way up until the experiment. So he didn't let anybody else look at it. Those numbers he would then give to an agent of his sitting in a room in some, say, studio. In that room there was a table, and in the middle of the table would be a screen with a hole cut in the middle of it, okay, a small square hole cut in the middle of it, which would allow that first agent to show these numbers one at a time to another agent on the other side of the screen. Okay, the setup was kind of like this. So agent 1 on one side of the table, screen blocking everything out except for a small hole, holding up a number. Agent 2 sitting on the other side of the table can see the number. And the second agent had a series of 5 cards, okay, with pictures of animals on them. And the animals were an elephant, a giraffe, a lion, a pelican, and a zebra. Okay, so 5 cards with these pictures on them. And what they would do is shuffle up these cards, kind of randomize their order, whatever that means, deal them out face down on the table in front of agent 2 so that only he could see them. And then whichever number the first agent showed him, he would pick up that card. Okay, so this was sort of card 1, 2, 3, 4, 5, going from left to right. Pick up that card, look at the picture of the animal, and just think intently about that animal for some period of time. Okay? And meanwhile, Gloria Stewart was maybe sitting in an adjoining room in this building, unable to see what's going on in the first room, but trying to imagine or use her telepathic abilities to understand what animal the second person was thinking about, and then writing down a list of guesses. Okay, so Stewart would have these guesses like, elephant, lion, giraffe, zebra, whatever. Okay? Then, after some number of iterations through this, so it's basically some number of agent 1 showing a number to agent 2, thinking about an animal, Mrs. Stewart guessing what animal it was, they would reveal the permutation of these cards. Okay, so the order that they had been shuffled and dealt out in. They would translate her guesses back into numbers. Okay, let's say that was 1, 1, 3, 2, 5, okay, whatever it was, and then compare with the original sequence that Soal had given his first agent. Okay, that would make up basically a block of these trials, and then they would try it again, maybe with another. They do it 50 at a time, so they would do sort of 50 numbers with one shuffle, record the results, shuffle up the cards again, 50 numbers, etc. Okay. So basically the idea here is that there's some kind of strict separation in the information in the experimental setup, where Agent 1 and Soal were the only ones who knew the numbers, in particular kind of the upcoming numbers in the sequence. Agent 2 just knew the number for that single trial that he was interested in, and was the only one who knew at the time how that number corresponded to an animal picture. And then Gloria Stewart was supposed to be telling them what animal Agent 2 was thinking of as they went along, but she couldn't see anything about what was going on in the first room. Okay, all of this was supposedly, witnessed and verified and audited by very reputable people and people in the scientific community who maybe were skeptics and just observed all the happenings and the goings on and made sure that it was all above board. Okay. And the kind of amazing thing is that they did this a very large number of times, and then in the end, in the final tally, Stewart was able to guess 9,410 cards correctly out of a total of 37,100. Okay, so it doesn't seem like that compelling of a figure that basically she got, some number of them right and a whole bunch of them wrong. Certainly not like our Mr. Smith example where he got all of them right. But what this works out to be as a percentage is about 25.36%, okay, which is higher than the kind of chance expectation that we would expect to get. So on our hypothesis of, let's call it HC, which is our pure chance hypothesis, okay, the one where she has no information about the sequence of the cards, we would expect that the ratio that we should have is about 20%, okay, because she's only got a 1 out of 5 chance of guessing each one, and we would expect that those are independent of each other. So actually we can write down, if we believe that that pure chance hypothesis is equivalent to sampling with replacement problem, the probability of getting, say, R successes out of n trials, we know. Okay, and that's just a binomial distribution argument from the sampling without replacement, and it's n choose R times the probability of a single one to the R times the probability of failing to the n minus R. And if we plug in the actual values for that were realized in this experiment, what we get is 37,100 choose 9410, okay, whatever that is, times 0.2 to that very high number times 0.8 to the difference of those two, which is 27,690, and that works out to be a number about on the order of 10 to the minus 139. Okay, Jaynes does a kind of approximation to get to this number in terms of Stirling's formula. Okay, don't worry about that too much, except just that it's an extremely small number. Okay, now remember that getting a very sort of improbable set of data conditional on some hypothesis is not necessarily a problem for us, okay? As we talked about with the widget testing example, doesn't necessarily mean anything except if there's some other hypothesis that would give us a much higher sampling probability, then we're going to have some evidence to support one hypothesis over the other. Okay, and the sort of class of hypotheses that Jaynes suggests we consider is what's called the Bernoulli class. Okay, so the Bernoulli class would be all the other possible hypotheses of the form HQ, where HQ just means that she has an independently probability of Q of guessing each number correctly, or guessing each card correctly. Okay, so this pure chance hypothesis is actually in the Bernoulli class. It's the H.2 hypothesis in that class. And if we just think about other possible hypotheses in that class where maybe through some kind of strength of telepathic ability, she was able to raise her performance to the point where she had a higher probability than 20% of guessing each card, then we have some hypotheses that we can test against. And the one that actually explains the data with the highest probability is the one HF, where F is this realized fraction of successes to trials. Okay, so we saw this a little bit with the widget testing example, where if we had an ignorance prior on all the different possible ratios of widgets in the box, our posterior probability assignment basically gets to be a narrow peak around the ratio in the sample. And that's kind of what's going on here. So the hypothesis in the Bernoulli class that has the highest likelihood of producing this data is the one that has the individual success probability equal to the realized fraction, okay? And if you do the same calculation we did up here and ask how likely is the data given that hypothesis, okay, there's some background information here I forgot to mention or to specify, but if we ask them conditional on that one, what do we get? Well, it's the same basically binomial distribution with a different fraction in here, and it comes out to be a number about 0.00476. Okay, so compared to the probability from the pure chance or 20% Bernoulli hypothesis, we have about 136 orders of magnitude higher probability for this, given this hypothesis than given that one. Okay, so what that means is that in doing a hypothesis test, let's say that we were just testing chance against this one Bernoulli alternative, we would end up supporting this hypothesis to an extreme degree. Okay, so if we kind of write that out just a bit more explicitly, we might say, okay, our probability of the data, as always, is, let's say we restrict ourselves to just these two possible hypotheses, chance and HF. So that's data given H chance times its prior probability plus the data given this heightened fraction HF times its prior probability. Okay. Just to simplify the notation, this is something that Jaynes says too, this number here, okay, probability of the data given a hypothesis, that's usually called a likelihood, okay, and likelihood just means thinking of it as a function of the hypothesis. So we're going to denote that LF for the likelihood of that hypothesis, meaning probability of the data for that hypothesis. So that's LF. This number would be LC. Okay, same thing, but for the chance hypothesis. The numbers on the other side over here are the prior probabilities, and we'll call those PF and PC for prior probability of the sort of highest probability ratio and the chance hypothesis. Okay. So again, if these were the only two possibilities, then conditional on this data, we know how to do the hypothesis test or assign the posteriors, and it's just each of the terms in this expression divided by the total. Okay, we saw that last time. So, in particular, our posterior assignment for the heightened fraction hypothesis, given the data, is going to be something like the second term, LFPF, divided by the sum, which is LCPC plus LFPF. Okay, but now you can kind of see that actually the priors don't really make much difference. I mean, assuming that we had any kind of uncertainty at all as to whether this hypothesis was true, and we assigned it any kind of reasonable prior, even like our 100 decibels against prior, okay, our 10 billion to 1 shot against, this LC is going to kill off any prior association we had to the chance hypothesis, but just because that number is so small in comparison, especially with LF, which is the likelihood given this alternate hypothesis. Okay, so kind of no matter what priors we associate, this number is going to be very, very close to 1. It might have like 100 nines in a row after the decimal point. Okay, so well, that seems very convincing, and that's certainly what Samuel Soal and his collaborators would like us to conclude. And the question is, all right, do we agree with that? Do we follow that line of reasoning? And if we don't, then why don't we? And what is it that's preventing us from reaching this conclusion that, even given any kind of uncertainty we had in our priors, the likelihood of the data basically makes it so that we have to be certain. Okay. And the answer to that is that actually we know that these are not the only possible alternative hypotheses that might be going on to explain the data. Okay. Now we kind of mentioned one of them earlier with Mr. Smith, and we make it a little bit more clear here. So there's one alternate possibility, which is that maybe these numbers that Soal was coming up with were not really kind of sampled with replacement in the right way, and they didn't have kind of equal proportions of each number being represented. And it may just be that whatever his favorite number was to write down happened to correspond to Gloria Stewart's favorite animal, probably the giraffe. And maybe his number is 3, and so maybe it just happened that those two numbers lined up a large number of times, and that gave her this kind of higher realized fraction. Okay, we could probably dispense with that if we were able to find out more information about how he generated the numbers, or audit them and check that actually they had equal ratios of each number 1 through 5. In fact, it's a little bit weird in the experimental setup that it should even matter, because we have this kind of double randomization where we have a random sequence of digits, and then those get translated randomly into a sequence of animal cards. But the whole problem there is that we're reusing the same permutation for a block of numbers just kind of for time's sake. Okay, so if they had done probably the right thing and just reshuffled the deck every time, then it really wouldn't have even mattered what the sequence of numbers was. They could have told Gloria Stewart what numbers they were, or that they were just taking the top card off the deck each time, and it wouldn't have made any difference because the deck's still being shuffled each time. Okay. Now, why they didn't do that is probably just to save time, because they had to do 37,000 trials. But maybe we'll just ignore those possibilities for the time being. But there are many other possible hypotheses that we can imagine and kind of conjure up. Okay, so maybe it was the case that Stewart had some system of mirrors set up so that she could kind of see into the adjoining room somehow, or maybe it was that she had someone signaling her, so one of these observers was actually kind of her associate and was looking over the shoulder of the agent and could see what the card was and was kind of communicating that to her somehow. Many other possibilities like this. Maybe Soal and his collaborators actually kind of doctored the data, just kind of misreported their results, which actually is what turns out to have happened, but we'll get to that in a minute. Or many other things. Okay, so basically we have maybe in the back of our minds some third hypothesis, which we'll just call HD, which we can generally label deception. Okay, deception or experimental error or bias or something going on that is some other hypothesis besides just pure chance and the possibility that she has ESP. Okay, and if we think about then what this posterior probability calculation would look like if we had some other hypothesis HD with its own prior and its own data likelihood probability, what would it end up being? Well, we'd have probability of, again, our ESP hypothesis would now be something like that same first term, but divided by a sum of 3 things, because we've got 3 possible cases where we have LCPC plus LFPF plus now this third term, which is LDPD. Okay, likelihood of producing the data under some assumption that something fishy is going on, times the probability that we associate to that as a kind of prior probability. Okay, now it's still going to be the case that this data is extremely unlikely under PC, so under hypothesis of chance. So basically, we'll kill that off. And now, if it's the case that we think that the data are kind of just as likely under this deception hypothesis as they are under the hypothesis of just kind of guessing with a slightly higher rate of success. So we would write that as, let's say, if LF is about on the same order as LD, then this number works out to be what? Well, LF, and LD, we just sort of cancel those through because they're about the same number. And we have PF in the numerator, and in the denominator we have PF plus PD. Okay, prior association for the ESP hypothesis divided by prior probability plus of that plus prior probability for the deception hypothesis. Okay, and this is the point that Jaynes makes, which is actually kind of really what I think is going on here. If you don't accept the conclusion of this experiment, is that your prior probability assignment for this deception hypothesis, okay, however you define it, is probably going to be much higher than your prior assignment for the hypothesis that this woman has ESP. Okay, so it doesn't really matter too much what the numbers are, but if you assume, let's say that this number was 1,000 times higher than this number, right? Maybe it's, this is 10 billion to 1, and this is 10 trillion to 1, or something like that. Then that kind of puts a natural ceiling on how high this posterior probability could ever be, even after having observed this extremely unlikely data. Okay, this very suggestive data that would kill the chance hypothesis utterly, right? So the only thing it can do is raise the probability of the ESP hypothesis up to this kind of cap where it's capped by its ratio to 1 plus the deception hypothesis. Okay, so this still might be a small number, very close to 0, if our prior assignment for PD was much, much greater than our prior assignment for PF. Okay, and that's the point, right? So, if, let's say, again, it was like 1,000 to 1, then we'd end up at most thinking that our chances were 1 in 1,000-ish that we have someone with ESP. Now, that may seem like kind of a miracle, and we've maybe seen that in the course of doing this, we could elevate our ESP hypothesis from this, minus 70 or minus 80 decibel prior to something like 1 in 1,000. Okay, just using those same numbers. But actually, we have to kind of split these two examples apart, and we're not really completely capturing everything. Okay, when we talk about this Bernoulli class, really we should be distributing our prior for someone having ESP in some way across that whole class, right? So we picked one of the possible fractions of success out of that class. All of those collectively probably make up of what we think of someone as having ESP, especially the ones greater than 20% and higher. Although actually, come to think of it, we probably should think that if someone can reliably guess at lower than 20% correct, then they probably also have ESP, right? So there's maybe two sides of this. The only one that wouldn't correspond to ESP is kind of right at 20%. So, okay, maybe fractions on either side of that collectively make up our total prior probability that someone has ESP. And so actually the prior for HQ should be much, much smaller. It should be, some minuscule fraction of that total, maybe 1,000,000 to 1 or 100 million to 1 or whatever it is, prior probability. And to really treat this correctly, I think we'd have to do a continuous parameter distribution. We'd have to talk about the beta distribution and do things kind of in calculus terms. And we'll come back to this later. But anyway, that's why I think this is still a very, it doesn't help us out too much with this ESP hypothesis. Okay, we're probably going to have much, much greater deception prior probabilities than we are probabilities of someone having ESP to exactly this degree shown by HF. Okay. And actually, the analysis could be extended to some other possibilities as well. Okay, including, let's say, the possibility that LF is, let's say, less than the deception likelihood. Okay, so this is the likelihood of getting the data under this assumption that this person has ESP to exactly this, Bernoulli degree defined by this exact fraction. What if it's the case that that number is less than LD? Well, then actually, I think what you'll see if you play this out is that our posterior assignments can actually go down. Okay, and if we think about this, maybe in just a slightly different example, which would be, let's say that we were observing a magic trick. Okay, and the observations of the magic trick involve the magician performing something that is very unlikely. Okay, so we have three possible hypotheses, let's say, that we are considering testing. The first one is that this person doing the trick is actually magic. Okay, so they actually have magical abilities. The second hypothesis is what we'll call pure chance. Okay, and that is just that whatever happens is by luck accident. Okay, there's nothing really deliberate going on. And the third hypothesis, let's call trickery. Okay, meaning that something is going on behind the scenes that we're not able to observe, but we just think that it's possible that there's some setup that is causing these results to happen. Okay, and let's say that it is the case that the probability of the data conditional on this chance hypothesis is something very, very small. Okay, so something about in the order of 0. Okay, and these all have some priors and some likelihoods. So we have prior for chance, prior and likelihood for magic, for chance, and for this trickery hypothesis. Okay, and when I say probabilities, I mean conditional on the background information that gives us all of these priors and likelihoods. What does it then kind of play out to be for our posterior? Well, our posterior probability assignment for, let's say, the magic hypothesis, given the data, is going to be something like what we had before. It's going to be like PM LM divided by PM LM plus PTLT. Okay. And so all that really has to happen for the magic trick to be successful is that this number ends up being something about on the order of a half, right? So no matter what prior assignments we made to, being a magic trick or it being, actual magic or being some designed illusion, if it's the case that after doing this kind of data observation, we elevate that posterior probability to be about a half, then we're uncertain. Okay, so how could that happen? Well, that can happen if, first of all, let's just assume that if it's a trick, it perfectly explains what we're seeing. Okay, the magician just needs to basically increase this prior probability of magic, right, and decrease this prior probability of it being a trick based on what's shown in the course of the illusion, and needs to argue somehow that magic would produce exactly this number, or would produce exactly these observations. Okay, so the likelihood under the magic hypothesis is 1. Okay, so this is where magicians kind of make their living, and I think it was Teller of Penn and Teller, a magician duo, who said that actually all that you need to do to be a successful magician is design a trick in such a way that the explanation for how you did it is so unlikely that someone is seriously willing to entertain the possibility that you have magical abilities. Okay, so that might be something like, it requiring you to have gotten 52 decks of cards together and pulled out one card of each deck to make a complete deck of the same card. Okay, some huge amount of effort, or designing some box or some system of mirrors or whatever it is, that just takes a lot of time and effort. That, however much effort that requires, just reduces the prior probability assignment that someone might have that this is a trick, that a trick, a designed illusion could produce these observations, and maybe they play up in the course of the patter of the trick the possibility of magic. Okay, so for the ESP example, this would be something like, all right, if we had some scientific theory about brain waves and electromagnetic fields and energy and maybe quantum entanglement or something kind of freaky like that, then we might play up the prior probability that actually these things are real, that it's possible. Okay, so we increase that one, we could decrease that one, and we make it so that under the hypothesis of it being a magic, actual magic, we would see exactly what we're seeing. Okay, if that's the case, then we're going to end up with posterior probability assignments about on the order of a half, meaning that our evidence is about 0, and we're pretty much uncertain as to whether it's magic or not. Okay, the way that you can reduce the possibility of magic is by making additional observations and including them as part of your data that would not be well explained by the magic hypothesis, but would be well explained by the hypothesis of it being a trick. So if, for example, you ask the magician, okay, can I look inside this box where you just made the thing disappear and maybe take it apart and look at its components, and they said no, well, the reason they said no is because it hides the illusion of the trick, it hides the deception mechanism, but it's not consistent with the assumption that they have real magic abilities. If they really had magical abilities, they would let you take apart the box to your heart's content. So they probably have some story as to why you can't, why it only works in this one way, or whatever it is. But all of those, all of that observation becomes part of your data, right? And this is the point. Once that's part of your data, then the likelihood function takes that into account and says, actually, okay, now the probability of observing that under the hypothesis that this is a magic trick is higher than the probability of observing that, assuming that this person is really has magical abilities. And so we'd be led to conclude that the probability of magic actually goes down to be about on the order of 0 if this numerator and the denominator become small in comparison to the second term in the denominator. Okay, so I guess basically the point of this is that by playing around with the different terms in these expressions, you could imagine how someone could be led to one conclusion or another, right? Because they have different either prior probability assignments or data likelihood assignments, and they end up concluding one hypothesis is true or another hypothesis is true with very high certainty, and it's all just a function of the background information they have, what they know about the situation and what data they're able to gather and how that kind of updates their probability assignments. And I think that the other kind of lesson there is that some of those assignments are going to be wrong based on wrong assumptions about the reliability of the person performing the trick, or what's going on behind the scenes, or about things being impossible or possible. Okay, so the kind of theme throughout here, I think, is that the data of any problem really should encompass all of the things that you directly observe as the person assigning probabilities, and not just what someone tells you, right? So the data might be X experimenter or magician told me this is what's going on. That's my actual observation, but that doesn't necessarily mean that it's true if I believe that person might be unreliable. Okay, so Jaynes works this through in a couple of other examples, including things like courtroom evidence. So basically, how likely is it someone committed a crime based on evidence supporting that they had a motive, or that they were in the area at the time. Or you could think of it for things like political news, where people might reach different conclusions and actually diverge in their opinions based on observing the same data, which is the reported news or reported events of the world. And the reason that they reach those divergent conclusions is that one person thinks that the person doing the reporting is unreliable, right? So it's not evidence in support of the hypothesis, just evidence in support of the claim that that person is deceiving them, right? Or they think they're biased, or they have some axe to grind or some agenda, right? So baking all of those assumptions into these probability assignments actually will show you that for some people, probabilities might move one way, and for other people, they might move the other way. And they're all behaving rationally and reasoning rationally. They just have a different kind of set of background assumptions that lead them in different directions. Okay, so political opinions and divergence of opinions based on observing the same data is one important phenomenon. Also, he gives the example of the discovery of the planet Neptune, where we basically had some observed evidence of the deviation of the motion of the planets, and you could either say that that was evidence against Newton's theory of gravitation, kind of Newton's laws, or it's evidence against the hypothesis that there are only so many planets, and end up supporting the hypothesis that there's another planet out there, which is what they ultimately found and called Neptune. Okay, so I think that the general kind of framework here for adjusting the terms in these Bayesian inference rules and seeing how they play out in terms of the posterior probability assignments is a very powerful one. And it gives you some insight into why it is that, under certain conditions, people might be led to one conclusion or another, and why in particular it is that we don't believe magic tricks or experiments like the Soal-Golding experiment that show that people have ESP or claim to. Now, one, I think, just aside to make here is that according to the orthodox statistical techniques that we're going to get into in the next couple videos, we would certainly have rejected the null hypothesis of chance under any of these scenarios, and we'd have no other hypothesis to replace it with. Okay, so an ordinary statistical significance test would just tell you, well, you got some very unlikely data. It must be that there's a real effect here, and the person probably has ESP because we reject the null hypothesis and we don't know what hypothesis to replace it with. In our framework, we do know what hypotheses to replace it with, and we can test against hypotheses in a particularly well-defined class. Okay, so we're going to come back to that. In case you're wondering, in the example of the Soal-Golding experiment, how it was that they were able to do it, I can tell you the explanation, which didn't come out for many years. Okay, this was a significant problem in the scientific community for decades, and it really wasn't kind of fully resolved until the late 70s, when it kind of emerged, the full truth emerged of how Samuel Soal had been able to pull off this deception. And the way that he did it was actually in the generation of those random numbers. Okay, so we had these sequence of numbers 1 through 5, translated kind of at random into a sequence of animals. And what he would do is he would start with that sequence of numbers. Okay, so whatever it was, 3, 1, 5, and then he would add some additional numbers to the list that were all 1. Okay, so he would have generated this original sequence according to one of the standard techniques of the time involving log tables or something like that, come up with this list of random digits, and then just thrown in some additional 1s here or there. Okay, then, all right, well, so far actually that's fine. Actually, there's no problem. Again, we said that because of this kind of double randomization, it shouldn't really matter what the numbers were because we're shuffling a deck to line these up with animal cards. But then what he would do is after the experiment was finished, okay, whatever Gloria Stewart had guessed, he would translate her guesses back to numbers that were supposed to line up with his original numbers. And if she had guessed a 1, he would leave it alone, okay, so that was counted as a success. And if she had guessed a 4 or a 5, he would change the number in his original sequence to match up with her guess. So basically he would draw over where there's a 1, he would draw a 4, okay, a 4 or whatever. And if he needed a 5, he would draw it over something like this. Okay, he would make a 1 into a 5 somehow. Okay, so in the end, he had this sequence of numbers that had an abnormally high number of successes, but only where his original numbers had been 1, 4, and 5. Okay, so we left these alone because she guessed correctly. He only had to fix this kind of a few places, it turns out, to get this statistically significant result. It was just, 3 or 4 here and there, but it added up to this very significant deviation. And what ultimately gave it away was the presence of all of these additional 4s and 5s and 1s in the sequence, meaning that they weren't truly kind of generated randomly, whatever that means, and the higher likelihood of success, meaning matching up with what Stewart was predicting when the numbers were 4s and 5s. Okay, so you might think, there'd be some variation in her abilities to discern different animal types, right? Maybe she can kind of perceive a picture of a giraffe more easily than a picture of a pelican, but it shouldn't have anything to do with what number it was that generated the animal especially because that permutation was being randomized. Okay, so that was basically the smoking gun that gave it away, that she had a higher success only for some numbers, and that there was these other numbers kind of populating the list. So that's how he was able to do it. Much like a magician, he had a trick that involved some artifice that just seemed like it took a lot more work, and it should have had a very low prior probability assignment, but it was in the end what explained it. So just think about that kind of generally, and maybe some of the lessons then of this line of reasoning. And I think that you'll see that this is a general kind of framework that applies to a wide variety of real world examples. The first lesson, I think, is that first of all, as we've said before, improbable data only really means something in the presence of an alternate hypothesis that explains it more probably. Okay, so it's only significant if there's an alternative hypothesis. Okay, so those numbers, what are called the data likelihoods, okay, the probabilities of getting a certain set of data conditional on hypothesis, play a huge role in doing the hypothesis testing. And I think we've seen examples now where you wouldn't necessarily reject or accept a hypothesis based on how likely the data was either way. Secondly, that the alternative to this, say, pure chance hypothesis might include a number of complicated things. Okay, so it might be complicated and include things like, that there's deception, that there's systematic error or bias, or some experimental setup has gone awry. Okay, the pure chance hypothesis is usually the one that we like to work with because it gives us the easiest to write down sampling probabilities, but rejecting that in favor of some alternate hypothesis requires us to know what that alternate is and what its sampling and prior probabilities are. Okay, so we're going to come back to this time and again. Okay, but there may be other things going on that are harder to identify and kind of understand the properties of in this alternative to just pure chance. Okay, in particular, in this problem, we identified just a class of hypotheses called the Bernoulli class. It's a very useful class to deal with, but it's not at all the only possible alternate hypotheses that could be going on besides pure chance. There might be things in terms of correlations, non-independence of the data. Maybe someone guesses right the first time, they're more likely to guess right in the second time, et cetera, et cetera. Maybe it was the case that someone could only guess the previous card. Okay, so what's called the displacement effect in the literature. Okay, that is a hypothesis that we now have not included in our alternate class. So if we wanted to test it, we'd have to throw it in there. Okay, third lesson is that our claimed sort of hypothesis of interest, the thing that we think that the experiment is actually demonstrating, may be in some sense buried in the noise or the kind of cloud of uncertainty of all of these other possible hypotheses. Okay, so if we want an experiment to show something very controversial and very unlikely, with a very low prior probability assignment to it, we need to design the experiment very carefully so that it distinguishes that one hypothesis from all of these other possible deception hypotheses. We have to control the experiment very tightly and allow people to understand all the mechanisms of it and all of the steps along the way, so that basically they can separate the priors and not have it be the case that the data elevates that whole kind of noise floor up, including the one we want, but also all these other hypotheses that we'd like to exclude. Okay, so that's just something to be conscious of, especially in situations where we're dealing with kind of testing or experimenting with very unlikely phenomena or very unlikely hypotheses. Okay, and just one or two more kind of points to make, I think, that are all present in this discussion, are that it's not just the data. That determines a hypothesis test, meaning it's not just that someone gives you a set of numbers and you can kind of conclude from that, yes, this is significant, or yes, it's not significant, or we accept this hypothesis or we reject it, because we need all these other things to really assign probabilities correctly, including our priors and our data likelihoods and our class of alternate hypotheses that we're testing against, etc. Okay, so we need, alternate hypotheses, and we need priors, particularly, before we can even think about doing a hypothesis test. And without that, the data are useless. Okay, the other thing I think just kind of embedded in that is that the data may be more than what you think it is, because the data might not just be the numbers that came out of the results of the experiment, but all the things that you are told about the experiment, including who's doing the telling and how reliable you think they are, and what things they're leaving out, and what answers they give you to further questions you ask about the experiment, and so on and so on. Okay, so it's not just the data, but the data are a lot. So the data actually should include everything you observe. Okay, that's another thing to bear in mind that we've seen play out in these examples. Okay, so our background information is kind of everything we bring to the problem. The data is also everything we gather about the problem, and it may all be relevant to doing the hypothesis test. Okay, and finally, just the last kind of point here, again, a lesson that we've seen many times is that different people may be led to different conclusions. Okay, and that's just kind of the ultimate consequence of putting all these things together, that different people with different prior backgrounds and different understandings of the workings of some experiment may, even on observing the same things and getting the same answers to all the questions they ask, may rationally be led to different conclusions, which just means that, science is not all that objective. It does have some degree of subjectivity to it, but the rules that govern moving from one probability assignment to the next are kind of fixed and objective if we all believe that we're reasoning rationally. Okay, so if we follow the rules of probability, we have natural safeguards against drawing conclusions that are kind of inconsistent with our prior expectations or our prior beliefs. But different people with different prior beliefs could rationally be led different ways. Okay, so that's just again kind of the counterpoint to this general theme. So that's it. That's a lot of big lessons to draw from some maybe seemingly trivial examples. As I said, next time I think what we'll do for the next video or two is jump ahead a little bit in the book. So we're going to actually look at some of the orthodox statistical methods, their historical background, the kind of thought process that goes into them. We'll try to understand how they work, and we'll see ultimately how their failure to really incorporate these lessons is going to cause them to break down and give us some kind of illogical answers for some particular problems and real kind of scenarios where we might be trying to do some hypothesis testing or some data analysis. Okay, so orthodox statistical methods are going to work pretty well in some kind of contrived examples. They're going to break down utterly as soon as we move outside that world. And what we ultimately like to kind of understand is where do they work, where do they not work, and what is it about their failure, in particular their failure to articulate the alternative hypotheses for any problem and the prior probabilities associated to those hypotheses that leads to the kind of breakdown of them as logical reasoning. Okay, so that'll be the next video or two.